Hi, I'm Dalton, and today I'm going to take a little bit of time to talk about Lab 1. This lab basically involved comparing the observed position versus time from an object that I moved, and then the predicted position versus time for the same object at a constant speed as predicted by a computational model. Doing this lab was a way to observe Newton's second law of motion, or the idea that an object's motion will remain constant unless there's some net force acting on it to change that. And just as the law states, this is pretty much what can be found after doing the experiment and looking at everything. So here is an image for the idea of what motion I was observing. What you're looking at here is just a small wheel-like object being rolled across a table. The meter stick in the background is just there for the scale and the tracker software to get accurate positions. But what we're really looking at here, the system, is the wheel object itself. After I applied a net force into the object, setting it in motion, or in other words, giving it its initial velocity. So now what we're going to look at is the graph that was generated by the tracker software, which comes from the real world video. So basically, this graph was created by measuring the position of the object every few frames advancing through the video as it moved along the table. And what this gives us is a real position versus time graph representative of the actual motion of the object that we can observe with our eyes from the video. So now we're going to go take a look at another graph. This one's coming from a computational model generated through GlowScript, which is basically just a way that we can use simple code to model the motion of an object. So here, of course, we're going to be assuming ideal conditions and setting the computation to use a net force of 0. So nothing should be changing the velocity. And what I got the initial velocity from is just calculating it from the real world observation and the tracker graph by just taking 2 points and doing a final minus initial to get the velocity. So now we're going to take a look at the code. And in this code, it's set up so that the object's position is checked at the same time intervals as the real world observation that was done with tracker, so that it's pretty easy to compare both of these models side by side or even at the same time. So that brings us to the next graph, where we can see both of these models being shown at the same time on one graph. And just for some quick clarification, the red line is the data from the GlowScript or computational model, and the blue line is the data from the tracker. So what we see is that the slope of the graph represents the rate of change, and those are nearly identical. So put in other words, the velocities are appearing to be exactly the same. So this is what we expect by Newton's second law, because without the presence of any net force acting, velocity should of course remain constant. It's important to note, though, that the slope of the line on the data from tracker may be ever so slightly different from the computational model, but that's something that's actually to be expected and could be a small bit of error. And the reason for that is that there are actually some forces acting on the object in the real world. Net force isn't 0. For instance, we have things like friction that exists between the object and the table, and the air resistance that's constantly acting on the object as it moves along. Here in this case, this net force may be very small, and that's why we see that the object's velocity seems pretty much constant over this small time frame. But it's important to realize that there technically is a net force on the object, and that velocity would have a more noticeable change if the time period had been longer, say 20 seconds instead. So now moving on from that, I want to take some time to address a couple of additional questions. The first one being, what would happen if the axis were flipped? So let's imagine that we take the positive x direction that was used in the shown graphs, and we change it so that that's now the negative x direction. All that's really going to happen is that the line would flip over the x-axis, as now the object is moving away at a constant rate, or in the negative x direction rather than positive. But it's good to realize all the points are still going to measure the same distance from the axis, and the magnitude of the velocity is going to be exactly the same, just in the other direction. And then there's another question that was asked, which is basically how the forces add up to give us the 0 net force that we ended up using in the computational model. The simple answer to this is that the forces don't really add up to 0 net force like we talked about, since once again, we're measuring the position after there was a force applied giving an initial velocity. There's no longer a force being constantly applied to combat the friction being exerted on the object by the surface in the air. So eventually, over time, there is going to be a force acting slowing down the object, but over this small of a time interval, there's really a negligible impact on the velocity. So it's pretty convenient to use a net force of 0 in the computational model, as that gets us extremely close to the real world observation without getting more error by calculating the wrong net forces. And overall, that pretty much sums up what we did in Lab 1 and gives some basic evidence to Newton's second law.